Hello, in this video we're going to look at the sign test, or specifically the univariate sign test. In the next video we'll look at the multivariate sign test. But in this video, the assumptions are that our observations from a single population, so X is distributed with some F, and this is the parameter of interest, that's the shift parameter. F is absolutely continuous and theta is the median. So without loss of generality, we're going to just assume that the median is 0 versus that it's bigger than 0. And really it could be, theta is equal to some value, theta naught, but then we could convert that into, some other random variable, x minus theta naught, and then that new random variable would have a median of 0 under the null hypothesis, and so that we'd be back in this setting. So the test statistic is we're going to count how many of our data are greater than 0. And if the median is 0, we'd expect this to be about half our data points. If the median is shifted, we're going to pick up all the ones that are, that are greater than 0, greater than the median and between 0 and the median. So it's actually going to be more than half our data. And so this can be written as an indicator function from the sum from 1 to n of Sxi, where S of x is 1 if it's greater than 0 and 0 otherwise. So this ends up being our count variable. And we like this one because then we're actually summing IID random variables, which then the central limit theorem will kick in eventually. So the rejection region is when S is too big, greater than some k. That's indicative that perhaps the alternative is true. But we pick the k such that the probability of our test statistic being greater than k under the null hypothesis is alpha. And since this is discretized, usually it's less than or equal to alpha, but our goal is alpha. So the distribution of S under the null hypothesis is each of these indicator variables is a binomial. We're either above x or above 0 or not above 0. And under the null hypothesis, being above is 50% or 0.5. So each of these S of xi's is binomial or Bernoulli with p equal to 1/2. And of course a Bernoulli is a binomial. So now if we add up these Bernoullis, we get a binomial. So we add up each of these, it's binomial n and 1/2. Now here's an important note. Note that S does not depend upon our original F. And to emphasize this, the F, I probably should say F of and then have a subscript H naught, which means it's the null, or it's the distribution under the null hypothesis, that our test statistic doesn't depend upon it. So that's why they call it non-parametric. Well, let's look at the distribution under the alternative region. So here we need to pick a theta greater than 0, because we're saying we're in the alternative, so the median is positive. And so now here's a note that in general, if we want a probability that x is greater than x, then it's a survival function. So it's 1 minus the CDF, and then but you have to put theta star because that emphasizes that this distribution is now the distribution that we picked in the alternative region. Okay, so now this right here is actually the distribution under the null hypothesis, but with the new median, so it's actually shifted. So these are the same. All right, so I wanted to emphasize that, and you may have to pause that and make sure that that's right in your mind before you go. So now let's look at the probability of being positive. And remember, because that's our test statistic, we're going to count up how many are, greater than 0. And so we're going to let P be this, but now we're under the alternative region, And so, you know, the little x is 0, so we put 0 here, and then this is our probability of being greater than 0. So now, each little indicator function is it's a 1, meaning greater than 0, it's with probability p. So this is a little Bernoulli distribution, or Bernoulli random variable, one, you know, with p. But this p actually depends upon the distribution in our, you know, under the alternative. And so actually the distribution of S under the alternative is not non-parametric. So when we add these up, you know, we sum them, we get a binomial of n and p, where p, of course, is the probability of being greater than 0 under the alternative. Note that S is not non-parametric under H1. So boom. And then you can do this to calculate power on, you know, given certain distributions. So the limiting distribution of S, which is, remember, we're counting things greater than 0, and this is our test statistic, so we're adding up independent, you know, IID random variables. So the central limit theorem says if we take S times its expected value divided by its standard deviation, that limits in distribution to a Z, which is a standard normal. So S, our test statistic, and the expected value of this is n times p, because we said this is a binomial, and the mean of a binomial is np, and the variance is npq, or np1 minus p square root. So this limits a distribution to Z, a standard normal. And before we leave, I want to point out a video that I think is worth watching, and that we prove that the sign test is the most powerful test in this setting. So what's kind of interesting, you don't go out and prove that it's the most powerful. In a given setting, you want to find the uniformly most powerful test, and so we seek to find that, and it ends up being the sign test. Anyway, I really think that's an interesting video to go back and watch. Well, that's all I have for today. Hopefully you enjoyed that. If you did, like the video and subscribe so you don't miss the next one. Thanks. Bye.